Before getting back to 5G, we'll do a short discussion on ICIC, Intercell Interference Coordination. It's an important part of radio planning. Uh, the key challenge for the radio planners is to mitigate the interference because you yourself generate the interference. Uh, you know, or I mean, cellular communication is most affected from uh, well, I mean, uh, one of the uh, well is the application where interference coordination becomes most challenging. For other applications like for LOS, interference is not a problem. And for Wi-Fi or for cordless phone or this kind of small applications, there are enough channels available. The cordless phone uses very small bandwidth, so it is easily configured with like say 40 channels. So it just checks which channel is currently empty or free. So it captures that and uses it. It scans uh, and finds out the free channel. Uses that. Wi-Fi also does similar thing. Multiple channels are available and selects the available one. So these things can easily handle interference of generated by similar applications, but or similar technologies. But in similar environment, you have to use limited bandwidth to support so many users in the country, and so you scatter your base stations and you have to manage it different. Now, what we'll discuss today is just the uh, techniques available for interference control in 4G or 5G. Okay. These techniques are not available in older generations. So, short presentation on ICIC, and then we'll go back to our previous discussion on 5G. Intercell interference coordination. Other cells around can be a source of interference for a particular cell. So, how you take care of them. And since we have smart techniques, the frequency reuse factor, say if we think of 2G, in 3G we use the same frequencies in every cell, but in the case of 2G we had to split the available bandwidth and allocate them to different cells because that's how you manage. But here the same bandwidth can again be like 3G. You can allocate to the adjacent cells just because your interface coordination is very smart. Okay. Uh, However, it's more common that you use three for frequency respect to three. It can be uh, called either 1/3 or three. Okay, both are conventions. So uh, you split the available. If you have 15 megahertz, you split into three parts. Each cell will get 5 megahertz. So you repeat after every cell. Okay, you you are using different resource blocks. Okay. Uh, since X2 interface, is available, you have interconnection, the nodes in the neighborhood, you can inform the two major techniques is the information sharing about the use of power in different resource blocks. And the second technique is to manage power level uh, differently on different resource blocks. Yes, sir. So these are the major ICSC methods, and these methods can be adapted. You can change them uh, statically or semi-statically or dynamically. How quickly you change them, it depends on the operator. Once in a while, some techniques you can change once in a while, some more frequently, some in every subframe you monitor and update your whatever you are using for your IC. Now, information sharing. For information sharing, we have two kinds, like sharing for downlink interference. So what you do in this case, a cell informs its neighbor cells. Um, sorry. You do, the exchange interface is used for the information sharing. It you let the neighboring cell know what level of power you're using in different parts of your, in different resource blocks. And usually this uses the indication of high power. For example, if you have some users in cell edge areas, and so you'll be using high power for them. Otherwise, you cannot communicate. So, in fact, these users are even closer to your neighbor cells. So they will be problematic. If the same bandwidth is used in the neighboring cell, then about these resource blocks, the neighboring cell has to be careful. You are communicating using high power, and so the users in the neighboring cell will also be receiving high, actually significant power on those resource blocks. Because I mean, you're communicating with your cell users, but since you have to use high power, that power will reach the neighboring cell. So users who are receiving on the same resource block will experience signal interference. So what do? You just let the neighboring cell know that I'm using high power here. I have to. And then the neighboring cell, uh, may, I mean, will do something. It may not use those resource blocks for that uh, particular period, or it may use those resource blocks for users who are close to the base station. Who knows who are close? Okay, yes, it has some idea. So somehow it will use this resource blocks, I mean, differently. So now for uplink interference, okay. For uplink interference, there are two types. Uh, like you can tell that yeah, it is going to create interference. I mean, or high power on these resource blocks. Again, it's for the cell edge user. And similarly, the neighboring cell will handle. Because the cell edge users uh, in the uplink when uses high power, then the neighboring base station will also receive significant power. So a similar problem, but now in uplink. The neighboring cell will can use, this cell, this resource blocks differently. Like before, it may use this resource blocks for, it may not allocate this resource block, however, whatever. It may allocate them for users who are close. Okay, so who if it uses for users who are close, the difference here is that when the user is in stallage areas, okay, on one side, uh, on the one hand, the user uses high power. On the other hand, the eNodeB receives relatively lower power. Okay. So for the neighboring cell, uh, I mean, say, uh, it receives significant power. Okay, but if it allocates the same resources to its own stallage user, then the power level will be almost equal. Okay. The I mean, power from the stallage users of another cell and power from the stallage users of its own cell, the intended user, will be almost same. But if it allocates the same resource block to the users who are close, then the power level will be higher. So in that case, the CINR can be okay or tolerable. So it may allocate to users who are close, or it may even avoid. Okay. It is possible if it is not very highly loaded, then it won't allocate those resources. The other part is that since the neighboring cell could also notify, we can view it from our own cell, that you may be receiving high interference on some resource blocks in uplink, and that's causing severe problem. Sorry, I got interrupted. Sorry, I get interrupted. So you can uh, inform them that these resource blocks are currently experiencing unacceptably high level of interference. So, kind of objection you can send. In the uplink, this is helpful because the users are scattered. In the downlink case, you transmit power from some fixed location, and you have better idea about what is happening around. Say, when you first deploy, uh, before deployment, of course, you do a lot of simulation, what may be happening really in the area. Also, when you first deploy, before you go for public use, you do some tests, optimization. Now, in that case, the the downlink is actually better understood. You clearly know what is happening in the area. you're sending far from, uh, I mean, pretty clearly know. Uh, Perfectly, you can never know what the radio signal status, but pretty clearly you can understand. From some fixed locations, you are transmitting power, and you know the directions, the radiation patterns of your antenna. From some tests also, you get good idea. But in the uplink case, the users can be anywhere. So even there are no tests that can help you find out what may be happening in the area. Okay. So from you can't even access every area, right? You may be moving by a car for your test, but inside buildings you can't access. But the user should be there and generating power from there. And so what will really happen in the update is not well known, and so you have less control. And in the for uplink, the eNodeB tries to control, set some uplink power level, commands whether it should increase or decrease power. But it is still under poor control. And that is why it may happen that you are receiving uh, some high level of power in the uplink, okay? Because the neighboring cell could not control some users well. So those resource blocks, the resource blocks will be contiguous after So the resource block used by some user, maybe one or two users, are actually, they are creating too high power. So you may actually send objections to that these resource blocks are very high. And so the cell will understand and reduce the when you use high power, okay, the same cell has actually no problem with that. High power you use better be reception for yourself, but it will cause problem to neighboring cells. Now the other type, other major technique of ICIC. Okay. So this will actually explain why it is possible to use so uh, low FRF, frequency reduce factor. In the case of 2G, we say that the typical frequency reduce factor was 12, right? We said that the typical number of cells are 4, n was 4, and you have 3 cells. So 12 is the typical frequency reduce factor in the case of 2G. It varies from deployment to deployment, but most commonly it is 12. However, in the case of LTE, most commonly it is 3, and sometimes it is just 1. So how is it possible? Okay, so we're explaining it just because the interface control is very smart. Now the other technique is fractional frequency reuse. You split the bandwidth, and basically for the cell edge areas, you allocate a part of your bandwidth and control them differently. Because cell edge is the problem, as we are discussing. The cell edge users are really good. Even for the last case, say you're objective about some resource block. Most likely they are cell edge users. Otherwise, why would they use very high power? And also that high power has to reach the neighboring base station. That's also possible when the users is close to his border. Okay. So it's also close to the border of the other cell. The cell edge users have a problem. Uh, so what you may do, you may allow a part of the bandwidth for users who are close. They are fine. They won't create problem to the neighboring cells. But for the cell edge, uh, And you can get this is called fractional frequency reuse, where you're splitting your bandwidth, and the fraction of the bandwidth you're uh, and there are different variants. Okay, so we'll show some of them, and for the purpose of explanation, uh, we are referring to this paper, which deploys, which shows deployment of femtocells as well. Okay. I mean, a lot of times you have some femtocell deployment also. So it uses some examples with both macro and femtocell. So let's see. So for example, here we are splitting the whole bandwidth on the right side. You see A, B, C, D. The whole bandwidth into three parts, into four parts. With one part A, little larger. Then what you do, the users who are close to the base station, are allocated uh, this part A. Okay? They are allocated part A. And the cell edge users are allocated B, C, or D. But this time you use frequency series factor actually 3. Okay. I mean, for the cell, for the users who are close, you are using FRF1, and for cell edge users, you are using FRF3. I mean, it's a mixture of 1 and 3. So that's how it overall FRF will be a little better than 3. You have some benefit on frequency, spectral efficiency. Okay. So say the cell edge users uh, are not using the same frequency. So you get rid of the problems that we were discussing in the early part of the class today. If you just see that if cell edge uses of the two cells, the neighboring cells are using different frequencies, then you don't have those problems. None of those, none of the problems we have discussed today. You don't have any of them. So this is a good solution. However, if you have some femtocells who are very localized, okay, inside buildings you use them, so then you can use, say, when you are using uh, the B chunk, okay, for your cell edge users, that B chunk you can still use inside for your cells inside. Okay. Well, it's not actually complete FRF. Okay. A completely FRF, it's not completely FRF1 for this, for the, sorry, I was mistaken. For the users who are inside are not using FRF1. It's not the whole part, it's a larger part of the bandwidth. Part A is a large share, but it's not the whole bandwidth. Another variant, the macro part, okay, the cell is just close to the base station are using, say, AB or AC or BC, and the cell is users are using the other. Split into three parts. Let again, uh, the key aspect is that the cell edge users have different frequencies. One is using A, the other is using B, the other is using C. So FRF is 3 for cell edge users. And the macrocells are using the rest part, BC or AC or AB. Now for femtocell, you use the alternate part. When macro is BC, femto is given A. When macro is given A, femto is given BC. In this solution, you have sectoring, and again you have large share A and BCG. Macro is using B, C, and D for the same edge users. So like before, the same edge users will have. So here you can see that we have different colors. If you look at the same edge users anywhere, uh, pink, violet, and white. The adjacent users have different colors. But the same edge, you have different colors. So that's the basic requirement. So nothing good. And for the inner part, let's see here, you allow the large share A. See, the large share. But entry users are scattered with again with whatever is split. Like when you're using D for macro, the rest three ATC are allocated to femto. Macro D, rest ACD. And similarly here inside also you allocate a part. Macro is using A, you use CD here. But you don't allocate D here because just I mean next to your in this region you have macro B. So there could be interference. So you use CD. So, the macro is using A and B. So this A and B part, A and B part is not allocated to any femtocell. The rest you allocate here CD and here the CD. Okay, so that there are more variants in for FFR. It's also possible that you allocate different levels of power. Or, I mean, you allocate some for select user, you allocate some resource block, and then you make sure that this resource block will be using lower level of power in the neighboring cell. So this is also a variant of FFR. But that actually means that you'll be using them for users who are close to the base station. Otherwise, lower power level cannot handle anything. So, uh, we didn't show the power levels, but um, uh, the basic concept is probably now clear. Questions? We'll go back to 5 minutes. Okay. We explain RC connectivity state and see that it's a mixture of, or it's somewhere in between RC connected and ideal state. Okay. So you can quickly go back to connectivity state. So it keeps the, when you are in RC connected state, you use some I mean, some set of information, some new things are settled, and on both sides, these are this information is stored. This is this type of information that you store is called context. So they, I mean, they can be for your access data, or they can relate to maths. So these are, I mean, math level concepts, AS level context. These are actually, I mean, these terminologies have been used since the 2D days. AS level context, NAS level context. So now, whether or not uh, you store them, in active state, you still store the context, so you can quickly go back. But what you do is you are not continuously connected, so you have to use cell reselection, or you have to use tracking area update like procedure, because you are not updating yourself. Whenever you're changing yourself, you are not updating. Once in a while, when you change the RAN notification area, then you update. So that's how you can enjoy actually. Uh, I mean, I mean, less resources will be consumed, and you will have longer DRX cycles. You can sleep longer. We are discussing the maximum data rate. How we can have this OH means overhead. There are many different types of overhead. Like say for control purposes of radio propagation purpose, you use different resource elements. So you need to subtract them. Anyway, so you see that the calculation gives you different. This is like how much bandwidth you are using. Now this is like, yeah, this is the bandwidth. Yeah, it's the bandwidth. Now there are four different modes. Okay, up to 4G there are two modes, FDG and TDG. But here it is also possible that you use data transfer only in downlink or only in uplink. Okay. So I assume that the applications maybe like say uh, mobile TV like applications can use. But uh, I mean, these provisions are available. So 5G comes with so many different uh, provisions to support the diverse necessities. When I looked at the spec, I mean, the recent spec, the major difference I found that a lot of lines are just inserted. Okay. When I wrote my book, I mean, uh, I was very, I was always delving into this page. Okay, so the difference to me is that a lot of lines are just inserted into the same spec with for different types of support, like for uh, IoT devices. Okay, low bandwidth and sometimes low bandwidth, extended coverage, CE. So this type of for this support, okay, you use this way, this specification, but for this case, the specification will be like this. I mean, you have some different different thing for different types of support. So a lot of lines are included. Now we let's see that frequency range up to 100 gigahertz is supported in 5G, but for now these two ranges are actually specified in the list of bands. There has to be a listed bandwidth for support, and different countries will allocate frequencies from the listed bandwidth, okay, to their operators. That's always the case. 3GPP specifies some bandwidth, and you have to select. Like this N1 is the common bandwidth for 3G and 4G in Asia, Europe, Australia. But there are many different bandwidths. The Pacific areas have differences in their allocation. USA has, North America has a different. So, they select different bandwidths. So I think it has to uh, uh, allow. Okay, we have to consider the necessities of all countries. Okay. So now you see for FDD, for TDD, it is unpaired. You do multiplexing in time domain. So you have a single frequency jump. And now you see that there are also some bandwidths defined for HDL and SQL. But when it is SDL, then for uplink you have nothing. For SQL, you have nothing in downlink. Okay. The term reformation is commonly used for frequency when you uh, chop it into different ways, okay, and then rearrange. That's called frequency reformation. Now, these two ranges, okay, I mean, these are the bandwidths, but they fall into this into one of these ranges, FR1 and FR2. So, our previous discussions also have this for FR1 and for FR2. They have different bandwidths available. Okay, now the subcarrier spacing has different options in the case of 5G. Let me show you why you have this option. It's not like if you uh, use say lower or higher subcarrier spacing, then your data rate increases. That's not the case because in the time domain, the symbol period has to be 1 over del f, right? The If it is 15 kilohertz, then the duration, okay, in the time domain, it has to be 1 over 15k, so 0.067 milliseconds. So if you use 30 kilohertz, then it is again 1 over 30. So for the two cases, I mean, if you, yeah, shown here. So, I mean, in the time frequency grid, you actually occupy the same space. So when for one resource element, this way in the frequency axis it is 15 kilohertz, and this way it is 0.067 or 45. So when you use 30 kilohertz, this way it will be shorter. The required symbol period will now be shorter because it is 1 over 30, just half. But this way it is not double. So you have the same space in the time frequency grid. So meaning that you have the same number of symbols transmitted per unit time. Okay. So in 1 second, you can send the same number of symbols, whatever your subcarrier spacing is. Now, 5G allows a number of options. Uh, the subcarrier spacing can be 15 kilohertz or 30 kilohertz or 60, 120. These are for data. 240 is not for data, it's for a control channel. So you can consider up to 120. So you have four different subcarrier spacing options. And the symbol durations are shown accordingly. Uh, uh, that Then why you have all these options? Well, it's because the uh, environment uh, has different types of multipath propagation properties. If you suit your environment, then uh, it's better. So different options are. So these are the four. 4 points are shown here. Uh, but the, the first point is like the delay speed can match better, or the surface spacing or however it is, you can match your environment better. Uh, Doppler frequency, these are not very important. Low latency requirement for short symbol duration uh, is also, I mean, that's also not very important, not very common requirement. You can send when you use high subcarrier spacing. You can quickly, if you have to send a particular number of symbols, you can quickly finish transmitting them if your symbol durations are shorter. So for low latency requirements, you can go for it. These are called numerologies. Okay. So this is the numerologies available. So here is a list, and you see that this 240 kilohertz is used only for some control channels. TDCH is the one that carries MIB, master information block. So it's a complete list of all uh, cost, all symbols, uh, length, and how much the periods are. And also it shows what frequency ranges we can support, and also what may be the use cases. We say that there are three types of use cases basically, or uh, target use cases. NVD, URL, and what else? So the third one, MMPC. Okay. Right. Okay. But the slot size is now a little different. Okay. Like for 15 kilohertz, we had um, I mean, two slots in every subframe. So in total, we had 20 slots. But in this case, you have 10 slots. Uh, this difference is used because for all numerologies, the number of symbols has been kept fixed. It's always coded. You see, this figure better explains. Uh, in 1 millisecond, the point is you have 14 symbols in every slot, but the number of slots will vary in, with your subclass schemes. So the symbol periods are varying accordingly. Say for 15 kilohertz, uh, we know that in 1 millisecond we can accommodate 14 symbols. It's known to us already. So now we call the whole thing one slot because we have 14 symbols. So in 10 millisecond or in a radio frame, the radio frame is still 10 millisecond long. So in 10 millisecond now you will have 10 slots. So that's the difference from 4G. In 4G you have 20 slots. So now you call slot different. And you don't call subframe. The term, oh, sorry. No, yeah. Okay, now in 30 kilohertz, you have two slots in the subframe because now you have symbols periods as half. So two slots are used here. I mean, with still 14 symbols in every slot. So in 60, you have 56 symbols, 4 times 14. So now you need to define 4 slots in 1 millisecond so that every slot still gets 1. So similarly, for 120, you have 8 slots. So in 10 milliseconds, you will have 80 slots. So the number of slots are like 10, 20, 40, 80. The symbol sizes are almost the same as we discussed in the case of 4G, that the first symbol was a little longer to fit in 0.5 millisecond. So that kind of requirement we also have here. A few symbols, you see the symbols, two symbols have some have little different length with all the other symbols and symbols of equal length. So the term slot is very more commonly used here. Okay, now for resource block, you see the bandwidth, you have to increase accordingly. For 15 it was 180 kilohertz, you know. If you allow 12 kilohertz, we still have 12 subcarriers. So 12 subcarriers. And a difference from the 4G concept is that for resource block, the number of symbols are not fixed. I mean, the frequency it is fixed. You have, I mean, for every resource block, you have 12 subcarriers, but the number of resource blocks the number of symbols for 4G was 7. But here you have to define how many. It can vary. So when you allocate resource, you also define uh, you define your resource block, but you also define how many symbols the resource block will carry. Give me a second. Give me a second. I want to show you something. The network architecture that I missed yesterday. Network, give me a second. Let me get it. Okay. In the case of 5G, to a provision is there to use something called centralized unit and distributed unit. Okay. In the case of 3G also, uh, the complete lower layers were split into base station and RLC. We discussed that there is an intermediate node called RLC in 3G. So the RLC layer was implemented in like PDC is also added. So that these layers were implemented in RLC. So when you transfer data, physical or MAC layers are implemented in the base station, but we also have RNC behind the base station, and then you connect to your core network. So the upper part of the protocol stack is implemented in RNC in the case of 3G. But later in 4G, everything was put together in the base station. Now, in the case of 5G, there is an option that you can have a centralized unit. Okay? I mean, the base station can have additional sort of splitting. Okay. A number of small base stations will be there who will implement the lower part. Okay. And upper part of the protocol stack will be implemented by the centralized unit. By lower part, we mean up to RLC, physical, MAC, and RLC. They will be implemented uh, by these small base stations. And then all these base stations will be connected to one base station, which will implement the upper layers of the protocol stack for all of them. Okay. So upper layers means PDCP, SDAP, and RC. So and even what you may do, you may just deploy the central the unit, the single unit under to which you connect all the small base stations. And you can have a contract with another vendor to deploy those base stations. So you can split the investment or the operation. As an operator, if you don't have enough capital for the whole operation or for the whole deployment, you can even split. So there will be different vendors who will join your operation, and they'll deploy few base stations in some places, and they'll connect to you. Deploy some centralized, the unit which is deploy the upper layer. So the units which implement the upper layers of the protocol stack are called centralized units, and the base stations which are many in number, which communicate with the UEs, are called distributed units. So C, CU and GU. So as you can see that there can be many in number, maybe 100 GUs. 100 GUs may be connected to a single CU. So CU will be more capable. You see that it will be more than 100 GU. More than 100 GU can be connected to a particular CU. So CU implements SDAP, RC, and PDCP. And GU supports the lower layers, physical, MAC, and so when you do that, looks like this. This can be taken. See the distributed units that is implementing physical, MAC, and RC, and central units. And I mean, PTCP you need for both control and user plane. But SDAP you need for your data user plane, and RC you need for your control plane, right? So you have two separate things. So we actually have this way. The splitting taking place this way. Where on Mac, I mean, you also have splitting. These are common terms that CUCP, you in the case of DU, you have L1 MAC RLC. Now in CU, you split. You have user plane and you have control plane. Okay. Then of course you connect to your core network using the two interfaces, user plane interface, control plane interface. And here also you have separate connections for user and control plane. So that you implement. So it's CPUP, control plane and user plane information, user plane separation for this type of implementation. So many different provisions are available. Right. Okay, questions? Uh, yeah. Common resource blocks are some, I mean, asset resource block. Uh, uh, and, you actually create bandwidth parts within your operating bandwidth. Uh, I got confused with something here. But, I think I need to click on it again. It looks a little different from what I thought of. Uh, let me check. Few things are added here, like say, for example, let me give you an example. We have 5 minutes. So, this part we will discuss the next day. Uh, but I need to check again. To tell you that, say for hierarchy procedure, we use some coding, and then on the other hand, on the other side, at the receiving end, if the packet is not, transmit block is not correctly uh, received, then you send the response. But when you use coding, actually you use very small, uh, small packets, and then you concatenate and create the whole transport block. Because coding, for coding purpose, each of the units has to have some uh, uh, length which is not that big. A few thousand bits or a few thousand symbols you have. For LT, the exact number I forgot, but it is something 4,000 something. So you actually have some limited number of, I mean, the actual, the these are called blocks. The blocks you use for coding purpose is pretty small. So a number of blocks are separately used for coding, and then they are concatenated to create the whole transport block. The receiving end uses again decoding for each of the code. If you don't receive that, I mean, when you send the response back or now, actually you don't have the luxury to indicate which code block you have failed to decode. The transport block may have say 10 code or say 20 code blocks. Okay. So you cannot indicate that I failed to decode these 3 code blocks from there, because that will be your acknowledgement overhead will then be higher. Uh, that's a that's a problem, right? So on the transmitting side, you think that okay, the whole thing may have been lost. Okay, so you send another version. Actually, that's another redundancy version. You try to soft combine. Uh, but it would be better if you could actually indicate which are not totally detected. So what has been incorporated in 4G somewhere in between, like for paging, we saw an option. Oh, okay, just give me 1 minute. I mean, something, an intermediate option is created. Some groups are created. Okay, there these many blocks, these many blocks, these many blocks. Groups are created, and for each of the groups, you send response. So the instead of well, single bit ACNet, there will be multi-bit ACNet, but not too many bits, not as many bits as you need to represent each of the code blocks. But you create some code block group, CBG, some code block group. For each of the groups, you send ACNet response in each of. So anyway, so let's again, I mean, let's stop today, and we'll, I'll talk to Samir to schedule some extra class. Okay, any questions? Questions? Okay, let's start.